annuities. So we've been talking throughout about investments, about compound interest, about compound periods. So far we've done large deposits up front as the principal, and then we let that amount grow and we see what's left at the end, or we know we want a big amount at the end, so we deposit a big amount at the beginning and we watch it grow and we hope we get to that future value that we're looking for. That's not generally how people invest. You might start with a lump sum, but then you're going to make regular payments toward that investment. Okay, and it's going to grow and you're going to receive interest on the initial amount that you invested, but you're also going to receive interest on the regular payments. But each regular payment is going to receive less interest because it will be invested for fewer compound periods. So we're going to make sense of this. This is what we call an annuity. We're going to make sense of this using some of what we've learned from sequences and series, as well as what we know about exponential functions. And here we go. So first we'll start by taking some first note at the top there, regular payments. Regular payments, these are payments of equal value made at equal time periods. Payments of equal value made at equal time periods, and this applies to both an investment where you're investing more at regular payments, or when you're paying off a loan. Okay, you might make those payments at regular intervals. Now, whatever you still owe is going to accumulate greater interest, but you're paying off. So what you've paid off no longer accumulates interest. So it's a great way to pay off a loan. Okay. Next word, annuity. Annuity is a sum of money paid as a series, there's that word, as a series of regular payments. So we're making the transition from a lump sum payment to regular payments. That's what we're dealing with annuities. Okay, a couple different types of annuities. We have an ordinary annuity. An ordinary annuity is an annuity for which the payments are made at the end of each payment. So payment at the end of each period. So payments made at the end of each period. So if it's made at the end of that period, that means that you're still going to have to pay interest for that period, or that it's still if you are investing, that means it's not going to gain interest for that payment period. That is different from a simple annuity, in which the compounding and payment periods are the same. Compounding and payment periods are the same. So that one's pretty easy to understand. If you have an investment and you're making regular payments and the compounding periods is, let's say it's monthly for 5 years, so 60 compounding periods, you're also going to invest that another chunk. You're going to make a regular payment 60 times. Okay. In an ordinary annuity though, if you are investing and you make a deposit at the end of a period, that deposit is not going to accumulate interest for that interest period. So you will have one fewer compounding periods than deposits. If you are borrowing and you make a payment against what you are borrowing, and you don't make that payment, you're not paying back that regular payment until the end of a compound period, well, you're going to get charged interest on the full amount for that compounding period. And then for the next compounding period will not calculate interest based on the full amount. It'll be the full amount minus your regular payment from the previous interest period. Okay. Hearing it all at once like that is probably a little bit confusing, a little bit hard to wrap your head around, but we're going to draw a timeline, take a couple more notes, and make this thing make sense. We'll apply it to some examples to solidify our understanding. First, our investigation. Colin is awarded $500 per year as long as he maintains a certain average mark for each of his 4 years of high school. Colin plans to deposit his award at the end of each school year into an account that pays 4% per year compounded annually. So we're going to assume that Colin does maintain the necessary average. So he's going to receive $500 at the end of each year, and he's going to make that deposit. How many times will he receive it? How many times will Colin receive $500 if he's getting it at the end of each school year? 4 years of high school, he's going to receive this payment 4 times. Will each of the $500 deposits earn the same interest? Well, if at the end of grade 9, he deposits $500 and he leaves that in for 4 years, it's going to accumulate interest for well, actually, he puts it in at the end of the first year. So it's only going to accumulate interest 3 times, right? And then at the end of grade 10, he gets another 500. That's going to accumulate interest to the end of grade 11, to the end of grade 12. So it's going to accumulate interest 2 times. Then at the end of grade 11, he's going to get another reward of $500. It's going to only accumulate interest for 1 year, so 1 time. And at the end of grade 12, he maintains his average, which he does. He's going to get another $500, which is not going to accumulate any interest by the end of high school. Okay, so they are not going to all earn the same amount of interest. We're going to have $500 being multiplied by our interest to the power of 3 plus $500 multiplied by our interest, 1 plus our interest rate to the power of 2, plus $500 times 1 plus our interest rate to the power of 1, plus the final $500, which is not going to accumulate any interest. So in step 3, we're going to determine a method of calculating that, which we've just kind of done. And now we're actually going to figure out how much is in his account. So here we go. We have, basically we're taking our future value formula and adding up all of the pieces. So here we go. We're going to do the future value equals present value, which is just this first 500. That is going to get multiplied by 1 plus our interest rate. I'm going to convert that to a decimal right away. We don't have anything else to deal with respect to our compound periods. It's going to compound annually, so only once per year, thankfully, which is the same number of deposits as he makes, but it happens at the end of the compound period. So this is an ordinary annuity situation. The payments are made at the end of each payment period. This first $500 is going to be compounded 3 times. Okay? The next $500 is going to be compounded at 4% 2 times. The next $500 from grade 11 is going to be compounded by our 4% 1 time. And the next one is not going to be compounded at all, but he's going to get that $500. So you could see how it would be 1.04 to the power of 0. Anything to the power of 0 is 1. Anything times 1 is just itself. And now we go ahead and step by step get those calculations and add up what we have. I'm going to let you go ahead and do that on your own. I would simplify this, then simplify that, then simplify each term, and then add them up. Do that and then come back and check how you've done. All right, hopefully you ended up with the same numbers that I have here. Basically, Colin, if he invests it in this way, so right when he gets the amount of money at the end of the year, he's going to chuck it in that investment account. So this is going to be, the first amount is going to be in there for 3 years. The next amount will be in there for 2 years. That's 2 compounding periods, then 1 compounding period, then 0 compounding periods. We take all those sections separately, we add them up. He's going to, at the end of it, have a total of $2,123.23. He will have been given, his deposits will equal $2,000. So you can easily see also the amount of interest that he's earned there is $123.23. Okay, let's take a couple more notes at the bottom, because one really helpful way to see this is actually by way of a timeline. And we have a bit of a timeline happening here, right? Where this amount it gets is the regular deposit, regular payment for 3 compounding periods, and then 2 compounding periods, and then 1 compounding period. So we have a timeline here already. Let's just draw it out to help us see it more clearly. All right, go ahead and start by drawing this timeline. Okay, at the top, we have our compounding periods. Okay? So we have now, and then the end of our first compounding period, the end of our second compounding period, and then all the way to the very end, our last compounding period, and we indicate the second last by n-1, and the third last compounding period is marked by n-2, okay? Now, what happens for each of these compounding periods? Well, at the end of each compounding period, we make a regular payment. That's indicated by capital R. Yes? It's indicated by a capital R. Now, what we also want to note then is how many compounding periods this amount of money is in the account. So we work backwards, okay? This regular payment is made right at the end of the last compounding period. So is it going to earn any interest? No, it's just going to be R. But this amount, this regular payment, is going to earn interest for 1 compounding period. So if it stays in for 1 compounding period, again, we're going to be working backwards. This one is R times 1 plus I to the power of 1. Okay? Well, let's see this third last payment. Third last payment. It's going to be in for 2 compounding periods. So we've got the regular payment. It's going to accumulate interest over 2 compounding periods. And we can go all the way down the list for all of these until we get all the way back to our first payments. I'm just going to go dot, dot, dot. And we'll bring this guy over. This payment is going to accumulate interest for how many payment periods? Well, look, it's the second payment that goes in. It's only going to be missing. It's going to accumulate interest over all the compounding periods except for 1, 2. Okay, so it's going to be in there for n minus 2 compounding periods. The very first regular payment is going to be in the account for all of the compounding periods except for the first one, because it was deposited at the end of the first compounding period. So it is going to have n minus 1 compounding periods. And now you can see that the amount of the annuity, so that's the amount of money in this thing at the very end of it after all of the interest has been calculated. The amount of the annuity, that's indicated by A, is determined by adding the amounts, combining my words here, the amounts of each payment. So again, all you're putting in is R, but this R is going to turn into R times 1 plus your interest rate to the power of the number of compound periods minus 1. This regular payment is going to be multiplied by 1 less compounding period. This regular payment is going to have 1 less, right? So you understand what's happening. So we're just going to add up all of these values in order to get the amount of the annuity. So what does that look like? A equals, well, what are we adding up? We're adding up just R is the first term. Second term is R times 1 plus I to the power of 1. Then we have our payment times 1 plus I to the power of 2 plus however many payments there are. Once we get all the way to the end of the list, we're at plus our regular payment times 1 plus I to the power of n minus 2 plus R times 1 plus I to the power of n minus 1. And there we have it. Since this is a geometric series now, okay, because we are adding we're adding terms, and to get from one term to the next, there's a common ratio. So we're going to say, since this is a geometric series with A equals R, so the first term, A equals R, and common ratio, so R equals 1 plus I, where R is the common ratio and A is the first term. R is the common ratio 1 plus I because that's the factor that's being multiplied by itself this many times, or this many times, or this many times, okay? So let's use the formula for the sum of a geometric sequence. The sum of the first n terms is equal to A, in brackets, R to the power of n minus 1 over R minus 1. Now you're really wishing that you had memorized this earlier. And we're just going to sub in the variables that we know now. So we've got the sum of the first n terms. We know A is R. And we know R is 1 plus I. So we're actually going to have to use a double bracket here. So I'm going to put a square bracket outside here. We've got 1 plus I. Close off that bracket to the power of n minus 1. That's just from right here. Close off the numerator. All over R minus 1, where R is 1 plus I. So we've got 1 plus I minus 1. Okay, this reduces. The only thing we can reduce right now is the denominator. You see we have 1 plus I minus 1. Well, 1 minus 1 is 0. So in the top we have the regular payment, square bracket, round bracket, 1 plus I, close it off to the power of n, minus 1, square bracket. There's our numerator, all over I. And here is our formula for the future value of an annuity when we know the regular payment, the interest rate, and the number of compound periods. And again, we use the term future value. So this is a little bit backwards from your perspective, but here's our formula. Future value equals the regular payment times 1 plus the interest rate to the power of the number of compound periods, and I is the interest rate per compound period, not per year, unless it compounds annually, over I again. Let's put this thing to use. Example 1. At the end of every month, Hoshi deposits $100 in an account that pays 6% per year, compounding monthly. He does this for 3 years. Okay, so it's exactly this type of scenario we talked about earlier, except there are multiple compound periods per year, so that's something to watch out for. And he deposits it like we did before at the end of each month. So the first thing we're going to do is draw a timeline to represent this annuity. In order to draw a timeline, we want to talk about what we know. All right, so we're using the same variables as always. The interest rate per compound period, well, we know it's 6% per year, that's 0.06, over 12 because we're compounding monthly, which gives us an interest rate per compound period of 0.05. Again, work carefully, work slowly, make sure you get everything that you need. How many compounding periods are there? Well, for 3 years, compounding monthly, 36 compounding periods. What's the regular payment? $100. Timeline. Now. 1. Skip a few. The last payment period is, we'll end it right there. It's the 36th period. So 35, 34. Okay, we know the value of n. Okay, the number of compound periods is going to be 36. So in here we skipped a bunch, ... What's happening here? He's making this deposit at the end of each month. So R goes in this row. Well, what's his regular payment? We know it. It's 100 in this month, in this month, and at the end of the 36th, he's going to pay $100 each time. But now pay attention to how it changes. The last $100 deposit does not gain any interest. It's just 100. Okay, I'm going to rewrite that in pink. But this $100 is going to accumulate interest one time. So our interest is, I'm going to just reduce it right away. The interest rate per compounding period is 0.005. So I've got 1.005 to the power of 1. This guy is going to be $100 times 1.005 to the power of 2. And then we skip a whole bunch in between. So those are all in here. And we take our first deposit, which is 100, and it is going to accumulate interest for every compounding period minus the first one, n minus 1. So it's going to accumulate interest 35 times. All right? There's our timeline. That's what we're doing. We've summarized our information. We have a graphical representation of it. Now we're going to determine the amount in the account after 3 years. And we're just going to, for B, use our future value formula, which says R square bracket, round bracket, 1 plus I to the power of n minus 1 square bracket all over I. Yes, you should be memorizing that formula. Okay, let's sub in what we know. We know he's going to make regular payments of $100. We know the interest rate is 1.05% plus 1, so 1.005 to the power of n, which is 36. And then we minus 1, and in the denominator we have our interest rate. We're going to divide this by interest rate per compound period, which is 0.005. And we work through this carefully. A really good way to do it is just think on the square bracket first. 1.005 to the power of 36, enter. Minus 1, enter. Times 100, enter. Divide by 0.005, enter. Okay? You end up with a value of 3933.61. How much interest will the annuity have earned? Let's do that in a second. First, let's write a sentence for B. Determine the amount. The amount in the account after 3 years is $3,933.61. C, how much interest was earned? So this is the full amount. That's all of the payments plus the interest earned on each payment. So we want to find out how much interest he's earned, which means we need to know how many payments he's made, how much has he paid into it. So how much of this amount is not what he paid into it directly? Well, since Hoshi made 36 payments of $100, his payments have a sum of $3,600, $3,600. Interest equals amount minus payments. All right, so interest equals the amount, $3,933.61, minus the $3,600 worth of payments, means he's going to come out with $333.61 in interest. All right, that's pretty good. So in this example, we were given the interest rate, we were given the number of compounding periods per year, so we were given the total number of compounding periods, and we were given the regular deposit. And all we had to do was solve, put it all in our equation, solve for the future value. Now, just like any other equation, we can use our algebra skills to use this same formula to solve for other parts, other missing information. We're going to see that in the next example. Example 2, we're going to be determining the regular payments. And this time we're going to have to find out what R is. Sadia needs $4,000 for university tuition when she graduates from high school in 2 years. She plans to make deposits into an account that earns 6.5% per year, compounded bi-weekly. That's pretty good. So once every 2 weeks. You can figure out how many times per year that is. A, again, we're going to draw a timeline to represent the annuity, and then we are going to determine her regular payment. How much money should she deposit bi-weekly if she wants to have $4,000 after the 2 years? So here we go. A, let's get our information down. Let's figure out what I is. We know she's getting, as a decimal, 0.065%. It's compounding bi-weekly. Bi-weekly means every other week, 52 weeks in a year. It's going to compound 26 times, which gives us an interest rate per compounding period of 0.0025. N, she's going to do this for 2 years at 26 compounding periods per year. There are going to be 52 compounding periods total. We don't know R, okay, but we do know A, or FV. The amount that she needs at the end is going to be $4,000. So let's go ahead and draw our timeline. We're going to start now. We're going to put the first period in there. We're going to represent a whole bunch of periods in between, and we're going to do the last 3 periods. Well, there are 52 payment periods. So 52, 51, 50. We do not know what R is. We know she's going to be putting it in at the end of each payment period. So we've got an R, an R, an R, and an R. We know that this R is not going to receive any interest. We know that this R is going to become R times 1.0025 to the power of 1. We know this R is going to become 1.0025 to the power of 2. We know there's a whole bunch of terms in between here. And then we know that our first regular deposit is going to become R times 1.0025 times n minus 1 times 51. There is our series or our sequence. And the last thing that we know about this situation is that these guys are all going to add up to our amount, to 4,000. Okay? All right, so we're going to use the formula for the amount of an annuity, and we're going to work with it, rearrange it in order to solve for our regular payment. Now, there's two ways to do that. We can rearrange the formula first and then sub in what we know, or we can sub in what we know and then rearrange. I'm going to just do it, well, I'll do it, substitute, and then rearrange, okay? So I'm going to take our amount formula, A equals numerator capital R times 1 plus I to the power of n minus 1 square bracket over I. I'm going to plug in the things that we know, okay? We know the amount on the left, 4,000. We do not know R. We do know 1 plus I, that's 1.0025. We do know n, it's 52. Close off my numerator. And we know I, 0.0025. Don't be tricked here, okay? In the bracket upstairs, 1 plus I. In the denominator, just I by itself, okay? It's going to be a very small number. How it happens when you divide by a very small number close to 0, well, the whole thing gets bigger, which makes sense, okay? Because our regular payment is going to be quite small in comparison to our total amount. That's the interest that it's going to represent. The difference is going to represent the interest earned. Okay, here we go. What am I going to do? I'm going to multiply both sides by 0.0025, okay? Multiply both sides by 0.0025, so 4,000 times 0.0025 is 10. And then on the right side, I just have the numerator remaining, 1.0025 to the power of 52 minus 1, close bracket. Now what are we going to do? We are going to divide both sides by this whole chunk. Okay, so we're going to divide both sides by 1.0025 to the power of 52 minus 1. Okay, this whole square bracket thing to isolate R. So we have, and I'm going to put R on the left here as well. So we've got R equals 10 over 1.0025 to the power of 52 minus 1. We can put that carefully in our calculator. That gives us a regular payment of $72.13. Okay, so Sadia should deposit $72.13 bi-weekly in order to have $4,000 in 2 years. Just quickly to the right here, I'm going to take this formula and rearrange it before subbing in. Basically, we're going to follow the exact same steps that we did here. We're going to multiply both sides by I. So on the left, you have A times I. And on the right, you have your regular payment times that big square bracket. And then we're going to divide both sides by the big square bracket. Again, putting R back on the left, we have A times I in the numerator, all over 1 plus I to the power of n minus 1. Now we don't need that square bracket. Okay, So in this setting, it would look like this, and then you would sub in what you know. You know A, you know I, you know I, you know N. Sub it all in, carefully calculate it, and you'll get the regular payment that she needs every other week is $72.13. This one was a little more difficult, but again, we just recorded all the information that we know and the information that we don't know. We made a timeline. In this case, we didn't know the regular payment, but we know that it's a regular payment. By definition, they're all exactly the same value, so we can use the variable r to represent that. We can see what happens to this r, this r, this r, this r. Add them up, 4,000. Use our formula carefully, calculate, work down. There you go. In example 3, we're going to be using the same formula. We're going to be determining the interest rate this time. Now, this gets a little bit tougher because we have an I in the numerator and in the denominator. So the way that we're going to do this is actually just set up our formula, and then we're going to graph both sides like we did last lesson and see where they intersect. So we have our dear friend Oliver. He plans to invest $2,000 quarterly for 5 years. $2,000 quarterly for 5 years. So his regular payment, $2,000. He's going to do this quarterly for 5 years. So N is 4 times for 5 years is 20. All right. His financial advisor informs him that his investment will grow to $45,682.40. So that's the amount. At the end of it all, he's going to have $45,682.40. We do not know what I is. So Oliver remembers some of the information, but he gets home and he's trying to explain it to his parents, and he doesn't actually remember what the interest rate is. So he goes to his math room. He has a designated room where he does only math. That's the only thing he does there. And he calculates the interest that he's going to be earning on this investment. And we know how to do it because we're just going to sub all of this information into our formula. I'm going to rewrite the formula one more time just for fun. 1 plus I to the power of n minus 1 over I. Sub in what I know, the amount. Left side, 45,682.40 is equal to a regular payment of 2,000, square bracket, round bracket, 1 plus I to the power of 20 minus 1 all over I. What are we going to do? Graph both sides. Identify point of intersection, POI. All right, let's head over to Desmos. All right, we are over here in Desmos. I am going to graph the left side of the equation. That is y equals 45,682.4. Then I'm going to graph a second equation, which is the right side of the equation. It is y equals, and I'm going to just bracket this whole thing, 2,000 times, double bracket, 1 plus x. I could type in I, it would probably be fine. I would probably figure it out. It's so smart, this Desmos thing. To the power of 20 over minus 1, close bracket, close bracket. I'm going to divide that whole thing by x, which I'm letting x be I in this situation. Hit enter. Okay, so now I should have two graphs. This is not going to be super helpful because my information is way up here at y equals almost 46,000. So I'm going to set my boundaries here to be right around there. 45,600 to 45,700. There's our line. And I'm going to just follow that down until I find, actually it's probably, I'm looking for an interest rate. So look, I can see right here, here's my blue line coming down and my red line, and here's where they intersect. Boom. The interest rate, they intersect at an I value or an X value of 0.0137. I'm just going to jot that down. They intersect Example 4, I'll help you get set up, then I'd like you to do some of it on your own. So Felicia plans to invest $2,600 at 6% per year, compounded annually. Thanks, that's easy. For the next 15 years. Compare the effects on the final amount if the deposits are made and compounding periods are. So first we're going to do annually, then we're going to check what happens if it's quarterly, then what if the compounded payment period is monthly, then what if the compounded period payment is weekly? So what's going to happen for each of these scenarios is the regular payment is going to happen more often, which means the regular payment is going to be much less, okay? Because she's still only depositing, investing $2,600 total, okay? What else is going to happen? Well, the interest rate per compounding period is also going to become much less, but the compounding periods is going to grow. All right, so we're going to use a table to organize some of the information. And right at the top of the page, I'm also going to just put my formula. The amount equals regular payment times bracket 1 plus I bracket to the power of n minus 1 square bracket denominator I. All right. Here we go. Table. Compounding period. And then our values for R, I, N. First, annual, then quarterly, then monthly, then weekly. All right. She is going to do this for 15 years. So the total amount she's going to be putting in is $2,600 per year. Okay, so if it compounds annually and she's putting in $2,600 per year, just one time at the end of the year, the interest rate is per compounding period, but it's only one compounding period per year, so that's the same as the annual rate as a decimal is 0.06. And how many compounding periods are there going to be? Well, 15 years, one per year, 15 compounding periods, okay? Let's look at what happens when we're dealing with quarterly. In order to determine the regular payment, we're going to take the amount of money, the regular payment per year, and divide it by 4, okay? We're going to split the year's amount into 4 pieces. That means she's going to deposit $650 every quarter or every 3 months. Same thing. Our interest rate needs to be the interest rate per compounding period. So we're going to take this amount and also divide that by 4. Gives us 0.015. That's 1.5% per quarter. And how many times is that going to happen? Well, now it's going to happen 15 years, 4 times a year, 60 compounding periods. Go ahead and use that in order to complete this chart. If you could just pause the video, press play when you're ready to double check your answers. Okay, for monthly, we're taking 2,600, dividing it by 12. That's going to give us $216.60. 67 cents. You notice we're rounding up there a little bit. That's okay. Our interest rate is going to be the 6% divided by 12 compounding periods per year, which is going to give us 0.005. How many compounding periods? 12 times 15 is 180 weekly. Now it's 52 regular payments. So this 2,600 gets divided by 52. And our interest rate of 6% gets divided by 52. Again, we want to leave a lot of decimal information. We don't want to round too early. I want to earn all my money, right? I don't want to skimp out on a percentage of my own interest. And N, how many compounding periods? 52 times 15 is 780. So there's the chart in our information. All we would need to do here is add a last column, call it amount. This is how much is going to be in our account at the end of the 15 years. And you're just going to use your formula here, plug in R 2600, I 0.06, and 15. Calculate it out, find the amount, change your numbers, calculate the amount, write it there, on and on to the very end. Okay, go ahead, pause the video, do at least one or two before continuing on and checking your answers. All right, the amount is captured in dollars. For this first one, if we type it in carefully, we end up with $60,517.52. If we were going to do it quarterly over 15 years, $62,539.52. So for not doing anything extra, you're not paying in, depositing any extra money, look at what happens to the amount. You earn over 15 years another $2,000 for doing nothing, just by finding the right account to deposit in. Well, yeah, the more compounding periods, the more times or the more often our money is compounded, it's going to grow faster, and exponentially so. Over 15 years, it made a pretty big difference. Think of it over 30 years or over 40 years. If you had the ability to start making small deposits right now, and you're not going to retire until you're 65 or so, that's almost 40 years or 50 years of compound interest being accumulated in your account. So let's see what happens if we're going to compound this thing monthly. We get $63,011.69. And if we compound weekly, $63,198.53. So again, the amount of the annuity increases. Let's make a note. The amount being the final amount in the account at the end of this period, investment period, the amount of the annuity increases as the compounding intervals become more frequent. Okay, so as the compounding intervals get shorter, as it compounds more, you're going to earn more interest on your money, which means your amount is going to be greater. Okay, in this case, the difference between an annual interest compounding annually and compounding weekly, for the same amount of money that you put in, you're going to earn an extra almost $2,700. Your practice problems for lesson 7.3 on annuities are from page 453, numbers 1 through 12. If you do get into accounting, you learn how to use spreadsheets and Excel to calculate all this. Excel has a lot of pre-formatted spreadsheets that are really helpful in calculating this stuff, particularly with regard to loans and mortgages, things like that. But go ahead and learn the basics, use the formula that's here, and use it to figure out any missing piece. Enjoy. They intersect at the left side and right side intersect at 0.0137, comma, 45,682.40. And now we interpret that, okay? What is our interpretation? Well, it means that the account is going to grow to its final amount at the end of the annuity when the interest rate per compounding period is, so I equals 0.0137. And actually, ours rounded and rounded down. The book has more accurate 0.01375. So I might need to tell Desmos not to round so aggressively. And then to determine the annual interest rate, to determine the annual interest rate, because it's always given as an annual rate when you're dealing with investments, we are simply going to do this strategy for finding I backwards. Typically, we would take, right, I equals, maybe I'll just do it here, I equals R, the rate per year, over N, which is the number of compounding periods. Okay, so in this case, we have 0.01375 equals R, which is the annual interest rate, over 20 compounding periods. Multiply both sides by 20, we get an interest rate as a decimal, 0.055, which is 5.5%. Double check that your answer seems reasonable. It certainly does in this case. That would still be a pretty good investment, getting a guaranteed 5.5%. And I'm just going to squeeze my final little sentence up here. So, Oliver earns interest. Oliver earns interest at a rate of 5.5% compounded quarterly, or 4 times per year. That comes straight from the question. There we go. So we couldn't do it just by applying our formula. We had to set up our formula and then graph left side, right side, find the point of intersection, and then interpret that. After that, that was just the interest rate per compounded period, which is not what the question asked for. It asked for what is the annual rate of interest compounded quarterly. So we had to take that, use what we know about interest rate per compound period, how it relates to interest rate per year, and do some simple algebra, get our interest rate of 5.5%.